Welcome all of you. Uh, I'm going to explain how to process data for conduction experiment. Okay. So as I have told you many times that just read the report requirements. Okay. So first of all, what you need to do is plot temperature profile at different time to show how steady state is achieved. So if you have data, I send you. If you have like this, so at different time, what does it mean? So first of all, this is linear conduction. So linear conduction, what we are doing, we are we have brass linear, okay, and we are applying the heat q at this position, and then conduction will take place in axial direction. So we are measuring temperature at different axial locations, for example here, 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 and so on. So T1 to T9. So at different axial position, this is known, right? If you see, it is like a different position is 0 0.1, 0 0.1, 0.02, and so on. So at 5 minute means after applying the heat flux, temperature is this from T1 to T9. After 10 minutes, it increases because we have increased the heat and so on. So if you plot all of them, this versus x, this versus x, this versus x, so what you will get something like this. So temperature versus x at different time. This indicates only one thing, that how the steady state is building. So for example, this is time t equal to 5 or 6, whatever, and then next 5 minutes it goes up to here. So yes, there is big difference, and after that difference is less, and after that is much lesser. It means that if we take data after this one, maybe both will be same. Okay. So this is what we said, this is steady state profile. Steady state profile. Okay, this is steady state. So we will need this equation, this graph, to get the slope and so on. So this graph only gives you the idea how steady state is building. So if you want to discuss this, you can say that as time increases, the profile are coming closer to each other. That indicates that we are reaching steady state. Okay. So each time you will use like the last data point at 25 or 30, whatever. This versus x will give you the steady state dt dx. Okay. So in case you have written like this, so this is a steady state profile. So you don't need to do this graph. Okay. So you have already a steady state graph, steady state data. So just plot them. So just plot them at t versus x. Okay, a different value of what. So if you, then you will get something like this, and then you can get the slope. So first value is like this is 28 watt. The slope is minus 409. Similarly, you can get the slope here and so on. So that is dt dx, and using that you can find k. So k is q is k a dt dx. So dt dx, you have it, the slope of the line, t versus x, t versus x. This is minus, right? So dt dx will be negative. Then the k you can find as k q over a dt dx minus. So for each data point, you can find the k. Okay, so what next? Plot steady state profiles for different apply head. This is what I told you. So this will look something like this. Okay, get the slope for all. Now apply Fourier law of heat transfer to find thermal conductivity of material and compare with that one mentioned in the by the supplier. So you find the K value at all data point as I told you using this and compare with the given value K. Okay, so this is all about linear, I think. Then radial. Radial, just to make sure that you know what we are doing in radial. Okay, we have inner cylinder. Okay, and we are heating at this point, and then we have outer cylinder. So heat will be conducted in this direction. Okay, and what we have here, T1 we are measuring here in the direction, T1, T2, T3, T4, T5, T6. So in this case, we expect that profile is not going to be linear. The profile also will be something like this. Okay, so if you look at the equation itself for the conduction, for the radial conduction, this one. Okay, so the profile LNR, so with R is logarithm, so you can fit a logarithm train line. So using this one, now it says that equation 4, find the thermal conductivity. So T0 is temperature of outer, Ti is the temperature of inner, R0 is the temperature outer radius, and Ri is the inner radius. Q is known. Okay, so this data, if you look at this, it is here. It's here. Outside diameter, so you can find the radius if you divide by 2, and same here. So using this equation, you can find the conductivity using radial. Like this one. Okay, and now what else we have requirement? Plot LNR. This is for radial data also. LNR versus temperature. Find the thermal conductivity of brass. So LNR versus temperature, what does it mean? If you look at this equation, okay, so LNR, then if you expand this LNR minus LNRI, so you will have basically Q LNR equal 2 pi LK, right? So if you this equation, if you see, so 2 pi LK, and then we have Ti minus 2 pi LK T naught equal, so this Q we can combine, so Q ln R naught over ln Ri. So if you uh, plot T means the temperature, yes, T means the outer temperature. For example, this one, Lenny, yes. So this this is the radial, right? T1 to T6. If you plot this T, and then we have this is R, and take the ln R. So in that case, ln r, find, like for example this one, ln r. So that's basically, okay, that's ln r. So now plot ln r versus t. Okay, ln r versus t. If you plot ln r versus t, the slope will be ln r versus t. The slope will be what? 2 pi lk, 2 pi lk over q. So ln r versus q. So radial, see, this is the question. Okay, so if you see this ln r, we expand this one, we will get this equation. Ln r naught minus ln ri, this is minus 2 pi lk, uh, 2 pi lk, this q will come here, right? This q. So we are plotting ln r naught, ln r versus temperature. This is the outer temperature, means the outer temperature. This is what we are measuring. So then what will happen? The slope will be, let me check the equation again. Sorry. This one is this is k, not q. K. And one minute, that equation. So yeah, this is q here. So equation is wrong here. One minute. So this is q and 2. Okay. So what happened now? See here, this will be minus 2 pi L k over q t naught and this term. So basically we are plotting this versus this. This is y. So this is x. This is x. So y equal mx. So this is the slope. This is the slope. The length is the thickness, right? Thickness. Pi the q, then you can find the thermal conductivity. So if you look at something like this, if you plot ln r, this plot, you will get something like this. ln r, this is ln r, okay, versus radial conduction versus temperature. This is the temperature, okay. The slope is this. You can see the slope is this minus 0.2066. So this slope you can find. This is the slope. So for example, in this case, I have minus 0.20. Then thickness is given L, pi, Q, the K you can find. Okay. So this way, we are finding the K by different methods. So if you can go back to the report requirements, Okay, so these are all report requirements. uh, okay, what are the boundary condition in both case? Okay, this is the final thing. So boundary condition, what are the boundary condition? So at one, for example, at here we are applying the heat, right, for linear conduction. At the outer we have water, right? So water is flowing like this to take the heat out. So at this point, x equal to 0, q equal q0, right? Q will be minus ka dt dx equal the value of q1 q0 whatever. This is known, right? So this is one boundary condition. At steady state, water is running like this, right? So water and the metal are in contact. So what will have happen? Conduction equal convection. So conduction in the metal k dt ka dt dx at x equal to L equal HA convection T minus T water, you can say. So this is the boundary condition. Okay, so that's it. I hope it should help.